Welcome to this comprehensive module on Kubernetes package management. Kubernetes package management is a fundamental skill for any DevOps engineer working with container orchestration. Throughout this module, we'll explore how package management solutions have evolved to address the complexities of deploying and managing applications in Kubernetes environments. By the end of this session, you'll understand not just the tools available for Kubernetes package management, but also the underlying principles that make these tools essential in modern cloud-native architectures. Whether you're new to Kubernetes or looking to optimize your existing workflows, this module will provide valuable insights into making your deployments more efficient and maintainable. Let's begin this journey into the world of Kubernetes package management together. Let's start by understanding why Kubernetes package management has become such a critical component in modern DevOps practices. When Kubernetes first emerged, teams quickly realized that while it solved many container orchestration challenges, it introduced new complexities in application deployment and management. Imagine trying to deploy a complex application with dozens of microservices, each requiring specific configurations, dependencies, and resource requirements. Without proper package management, this would mean manually creating and maintaining numerous YAML files, ensuring proper versioning, and managing updates across environments, a task that quickly becomes overwhelming. This is where Kubernetes package management comes into play. Think of it as similar to package managers you might be familiar with in other contexts, like apt for Ubuntu or npm for Node.js, but specifically designed for the unique challenges of Kubernetes environments. Throughout this module, we'll explore how package management solutions address these challenges by providing standardized ways to package, distribute, and manage applications on Kubernetes. We'll look at real-world examples and best practices that you can apply in your own DevOps workflows. The concepts we'll cover are essential for any DevOps engineer working with Kubernetes, as they form the foundation for implementing scalable and maintainable deployment strategies in production environments. The history of Kubernetes package management is a fascinating journey that parallels the evolution of container orchestration itself. In the early days of Kubernetes, around 2014 to 2015, teams were essentially writing raw YAML for everything. Each deployment required careful manual crafting of configurations, and there was little standardization across organizations. The community quickly recognized these pain points, and this recognition drove the development of tools to streamline the deployment process. The first major breakthrough came with Helm, which was created by DS, later acquired by Microsoft, in 2015. Helm introduced the concept of charts, packaged applications that could be easily shared and reused. This shift from manual management to structured package management marked a significant milestone in Kubernetes' maturity as a platform. It enabled teams to move from ad hoc deployment practices to more structured, repeatable approaches that we rely on today. Understanding this history helps us appreciate why current tools are designed the way they are, and how they address the fundamental challenges that have existed since Kubernetes' early days. Let's dive deep into why Kubernetes package management became not just useful, but essential in modern DevOps practices. The needs arose from real-world challenges that teams faced when deploying applications at scale. First, let's talk about the complexity of Kubernetes manifests. A typical application deployment might require multiple interdependent resources, deployments, services, config maps, secrets, and more. Each of these needs to be properly configured and maintained. Without proper package management, this leads to what I call YAML fatigue, the overwhelming task of managing numerous configuration files across multiple environments. The repetitive nature of deployments presents another crucial need. Consider a scenario where you're deploying similar applications across different namespaces or clusters. Without package management, you'd need to duplicate and maintain separate sets of manifests for each deployment, leading to potential inconsistencies and maintenance nightmares. Versioning and rollback challenges are particularly critical in production environments. Some incidents where teams struggle to revert to a previous known good state because they didn't have proper versioning in place. Package management tools provide the ability to track changes, maintain version history, and perform controlled rollbacks when needed. The desire for reusability and sharing of application configurations stems from the DevOps principle of not reinventing the wheel. When one team develops a solid configuration for a common component like a database or message queue, other teams should be able to benefit from that work. These needs directly influence the features we see in modern Kubernetes package management tools, and understanding them helps us make better decisions about how to implement these tools in our own environments. The significance of Kubernetes package management extends far beyond simple convenience. It fundamentally transforms how we approach application deployment and management in cloud-native environments. Let's examine each key aspect in detail. Abstracting complexity is perhaps the most immediately valuable benefit. Through templating and abstraction, package managers help teams manage complex applications without getting lost in the details. For instance, instead of managing dozens of individual YAML files, you can work with a single package that encapsulates all the necessary configurations. This abstraction doesn't just save time, it reduces errors and makes your deployments more reliable. Reusability through package charts has revolutionized how teams share and collaborate on Kubernetes configurations. Consider how the Helm community has grown. There are now thousands of pre-built charts available for common applications and services. This means you can benefit from the collective experience of the Kubernetes community rather than starting from scratch. Version management is crucial for maintaining stability in production environments. With proper package management, you can track changes, understand what was deployed when, and most importantly, roll back to previous versions if something goes wrong. This capability is invaluable during incidents where quick recovery is essential. Dependency management becomes increasingly important as applications grow more complex. Modern applications often require multiple services, databases, and other components to function. Package managers help ensure that all these dependencies are properly versioned and deployed in the correct order. The community contribution aspect has created a vibrant ecosystem where best practices and solutions are shared openly. This collaborative environment accelerates learning and innovation across the entire Kubernetes community. Understanding these significance factors helps you make better decisions about implementing package management in your own Kubernetes environments. Let's explore the landscape of popular Kubernetes package managers, each with its unique strengths and use cases. Helm stands out as the most widely adopted package manager in the Kubernetes ecosystem. Its success comes from its robust templating system, extensive chart repository, and strong community support. Helm can be successfully used in organizations of all sizes, from startups to large enterprises. It's particularly effective for managing complex applications with multiple dependencies. Kustomize takes a different approach as an official Kubernetes project. Instead of using templating, it focuses on configuration customization through overlays. This makes it especially useful for organizations that need to maintain similar configurations across different environments while keeping track of the variations between them. KubeApps brings a user-friendly web interface to the package management experience. It's particularly valuable for teams that prefer graphical interfaces over command-line tools, making it easier for developers and operators to discover and deploy applications without deep Kubernetes expertise. CAP, developed by the VMware team, emphasizes deployment workflows and visibility. It provides detailed insights into what's changing during deployments, making it easier to understand and troubleshoot deployment issues. This visibility is particularly valuable in complex environments where understanding the impact of changes is crucial. Scaffold focuses on the development workflow, automating the process of building, pushing, and deploying applications. It's particularly useful in development environments where rapid iteration is important and it integrates well with continuous deployment pipelines. Each of these tools has its place in the Kubernetes ecosystem, and understanding their strengths helps you choose the right tool for your specific needs. In many cases, teams might even use multiple tools together to address different aspects of their deployment workflow. While Kubernetes package managers provide numerous benefits, it's important to be aware of their potential drawbacks and challenges. Understanding these limitations helps you make informed decisions and plan for mitigation strategies. The complexity and learning curve associated with package managers can be significant. Each tool has its own concepts, terminology, and best practices to master. For example, when working with Helm, teams need to understand charts, templates, values, and the Go templating language. This learning curve can initially slow down teams and may require dedicated training time. Resource overhead is another consideration. Package managers add another layer to your Kubernetes infrastructure, requiring additional maintenance and monitoring. You'll need to manage chart repositories, handle versioning, and potentially deal with additional storage requirements for maintaining package histories. The lack of standardization across different package managers can lead to fragmentation in your deployment processes. If different teams within an organization use different package managers, it can complicate collaboration and make it harder to maintain consistent practices across the organization. However, these drawbacks shouldn't discourage you from using package managers. Instead, they should inform your implementation strategy. For example, you might start with a single tool like Helm for your entire organization to avoid fragmentation, invest in proper training to address the learning curve, and carefully plan your resource allocation to handle the overhead. Remember, the benefits of using package managers typically outweigh these drawbacks, especially as your Kubernetes deployments grow in complexity. Helm serves as the equivalent of apt or yum for Kubernetes, providing a standardized way to package and deploy applications. Just as those package managers revolutionized software installation on Linux systems, Helm has done the same for Kubernetes deployments. The beauty of Helm lies in its ability to take complex Kubernetes manifests and package them into charts, reusable version bundles that can be easily shared and deployed. This abstraction significantly simplifies the deployment process while maintaining the flexibility to customize applications for different environments. One of Helm's greatest strengths is its robust templating system, which allows you to parameterize your Kubernetes manifests. This means you can maintain a single chart that can be configured differently for development, staging, and production environments. Throughout this section, we'll explore how Helm works, its key concepts, and how you can effectively use it in your DevOps workflows. Whether you're new to Kubernetes or an experienced practitioner, understanding Helm is crucial for modern cloud-native development. The history of Helm is a fascinating journey that parallels the evolution of Kubernetes itself. Created by Dees in 2015, Helm emerged as a response to the growing complexity of managing applications on Kubernetes. The inspiration for Helm came from traditional package managers like apt, yum, and homebrew. The developers recognized that Kubernetes needed a similar tool to simplify application deployment and management. Just as these package managers made it easier to install and update software on operating systems, Helm would do the same for Kubernetes applications. A significant milestone in Helm's journey was its graduation as a CNCF, Cloud Native Computing Foundation, project in 2017. This marked its maturity and acceptance by the broader cloud-native community. The graduation process involved rigorous technical reviews and demonstrated Helm's widespread adoption and robust governance model. Helm has gone through several major versions, with Helm 3 being a significant redesign that addressed many of the security and architectural concerns of earlier versions. The removal of Tiller, the server-side component, in Helm 3 was a major improvement that simplified the security model and made Helm more Kubernetes native. Understanding this history helps us appreciate why Helm works the way it does today and how it has evolved to meet the changing needs of the Kubernetes community. Let's explore why Helm became such a crucial tool in the Kubernetes ecosystem by examining the specific needs it addresses. The fundamental challenge of Kubernetes complexity stems from managing multiple interconnected resources. Consider deploying a typical web application. You might need deployments for your application containers, services for networking, config maps for configuration, secrets for sensitive data, and ingress rules for external access. Managing these resources individually becomes unwieldy as your applications grow. Reusability is another critical need that Helm addresses. In a microservices architecture, you often need to deploy similar components across different services. For example, many services might require their own database instance. Without Helm, you'd need to duplicate and maintain separate configurations for each instance. Helm charts allow you to package these common components once and reuse them across your infrastructure. Versioning becomes increasingly important as your applications evolve. Helm provides built-in version control for your deployments, making it possible to track changes, roll back to previous versions, and maintain a history of your application configurations. This is invaluable when troubleshooting issues or when you need to revert changes quickly. The need for simplified deployment processes is particularly apparent in large organizations where multiple teams deploy applications to Kubernetes. Helm charts provide a standardized way to package and deploy applications, reducing the likelihood of errors and inconsistencies across deployments. Understanding these needs helps you better appreciate how Helm's features address specific challenges in Kubernetes application management and how you can leverage these features in your own deployments. Let's explore the core concepts that make Helm such a powerful package manager for Kubernetes. Understanding these concepts is crucial for effectively using Helm in your DevOps practice. At its core, Helm functions as a package manager, similar to how apt works for Ubuntu or Brew for Mac OS. It packages Kubernetes resources into what we call a chart. Think of this as a single versioned unit that contains everything needed to run an application on Kubernetes. Charts are the fundamental building blocks in the Helm ecosystem. They're essentially collections of templated Kubernetes manifest files that can be customized for different deployments. A chart might contain everything needed to run a complete application stack, from the main application to its database, cache, and any other required services. Templates are where Helm really shines. These are dynamic YAML files that use Go templating syntax to create flexible, reusable configurations. Instead of hard-coding values like resource limits or image tags, you can use placeholders that get filled in during installation. This makes charts highly adaptable to different environments and use cases. Values are how you customize a chart for your specific needs. Through values.yaml files or command line parameters, you can configure everything from resource allocations to application settings without modifying the chart itself. This separation of configuration from definition is a powerful DevOps practice. A release in Helm represents a specific instance of a chart running in your Kubernetes cluster. Each release has its own configuration and can be individually managed, upgraded, rolled back, or deleted as needed. The Helm CLI is your primary interface for working with charts and releases. It provides commands for the entire lifecycle of a Helm release, from installation to deletion. The Helm Hub, now part of Artifact Hub, serves as a central repository for sharing charts. It's a valuable resource where you can find pre-built charts for many common applications and services. Let's examine the key components that make up the Helm ecosystem, focusing on how they work together to manage applications in Kubernetes. The Helm client is your primary interface for working with Helm. Let's break down its essential commands. Helm Search is your gateway to discovering charts. Whether you're looking for a database, monitoring solution, or any other application, this command helps you find available charts in configured repositories. For example, Helm Search Repo Engine X, would show you all available Engine X-related charts. Helm install is where the magic happens. This command takes a chart and creates a new release in your cluster. Behind the scenes, it processes all the templates, applies your custom values, and creates the necessary Kubernetes resources. You can also use flags like -minus values to specify custom configurations or -minus namespace to deploy to specific namespaces. Helm Upgrade is crucial for managing the lifecycle of your applications. It allows you to modify existing releases with new configurations or chart versions. This command is particularly powerful when combined with -minus atomic flag for atomic upgrades or -minus install for creating new releases if they don't exist. Helm Rollback is your safety net. If an upgrade causes issues, you can quickly revert to a previous known good state. This capability is invaluable in production environments where downtime must be minimized. Helm Delete cleanly removes releases from your cluster, ensuring all associated resources are properly cleaned up. The chart repository component is equally important. These repositories store packaged charts, making them available for distribution and reuse. You can add repositories using Helm Repo Add and keep them updated with Helm Repo Update. Many organizations maintain their own private repositories for internal charts alongside public ones. Understanding these components and their interactions is crucial for effectively managing applications with Helm in your Kubernetes environment. Let's walk through the essential processes involved in working with Helm, from creating charts to managing releases in your Kubernetes cluster. Chart creation is the foundation of working with Helm. When creating a chart, you start by establishing a directory structure that includes your Kubernetes resource templates, default values, and chart metadata. Best practices include organizing templates logically by resource type, using helpers and named templates for common patterns, implementing proper template validation, including comprehensive documentation in the README. Chart installation is where your templates come to life in the cluster. During installation, Helm 1. Merges default and custom values. 2. Processes all templates with the final values. 3. Validates the resulting manifests. 4. Applies resources to the cluster in the correct order. The -minus debug and -ministry run flags are invaluable during this process for troubleshooting and validation. Chart upgrade process allows you to modify existing releases. This might involve updating configuration values, deploying new versions of your application, adding or removing resources. Always use -minus atomic for production upgrades to ensure atomic operations that roll back automatically if anything fails. Chart rollback is your safety mechanism. When issues arise, you can quickly revert to previous versions. Understanding the rollback process is crucial for maintaining system reliability. Remember that rollbacks restore both the chart version and values from the previous release. Maintain release history for audit purposes. Can be tested using -ministry run before execution. Each of these processes plays a vital role in the lifecycle management of your applications on Kubernetes. Let's explore the practical applications of Helm in real-world DevOps scenarios, focusing on how it solves common challenges in Kubernetes deployments. Application deployment is perhaps the most common use case for Helm. Consider deploying a microservices application with multiple components. Without Helm, you'd need to manually manage numerous YAML files and ensure proper deployment order. Helm simplifies this by packaging all components together, managing dependencies between services, providing consistent deployment across environments, enabling easy configuration management. CI/CD pipeline integration is where Helm truly shines. In modern DevOps practices, Helm charts become integral parts of automated deployment pipelines. For example, Jenkins pipelines can use Helm to deploy applications consistently. GitOps workflows can track chart versions in Git repositories. Automated testing can leverage Helm's -ministry run capability. Canary deployments can be implemented using Helm releases. Application versioning becomes much more manageable with Helm. Each release maintains its own version history, enabling easy rollbacks to previous versions, audit trails of configuration changes, consistent versioning across environments, simple A/B testing of different versions. Infrastructure. Provisioning extends Helm's usefulness beyond application deployment. Many teams use Helm to manage cluster-wide infrastructure components like monitoring solutions, Prometheus, Grafana, logging stacks, EFK/ELK, service meshes, Istio, ingress controllers. These use cases demonstrate why Helm has become an essential tool in the Kubernetes ecosystem. Welcome to our deep dive into Helm charts, the fundamental packaging format that makes Helm such a powerful tool for Kubernetes deployment management. A Helm chart is essentially a collection of files that describe a related set of Kubernetes resources. Think of it as a recipe book that contains all the ingredients and instructions needed to run your application on Kubernetes. Each chart follows a specific directory structure that Helm understands and uses to create reproducible deployments. Let's look at the basic structure of a chart, using a Hello World example. The chart.yaml file contains essential metadata about your chart. The templates directory holds the Kubernetes manifest templates. The values.yaml file defines default configurations. The charts directory can contain dependent charts. This structure might seem simple, but it's incredibly powerful. It allows you to package complex applications into a single unit, share configurations across teams, version your deployments effectively, maintain consistency across environments. Understanding this structure is crucial for anyone working with Kubernetes in a DevOps environment, as it forms the foundation for all Helm-based deployments. Let's dissect the anatomy of a Helm chart to understand how each component contributes to successful Kubernetes deployments. The chart.yaml file is your chart's identity card. It contains crucial metadata including the chart's name and version, a description of what the chart does, maintenance information, dependencies on other charts. This metadata helps users understand what your chart does and how it fits into their infrastructure. The templates directory is where the real magic happens. This is where you store your Kubernetes manifest templates using Go template syntax. These templates can reference values from your values.yaml file, use control structures for conditional resource creation, implement helper functions for common patterns, include partial templates for reuse. The values.yaml file serves as your configuration hub. It provides default values that can be overridden during deployment. Best practices include documenting each value clearly, using descriptive variable names, organizing values logically, providing sensible defaults. The chart.lock file, while automatically generated, plays a crucial role in dependency management by ensuring consistent versions of dependent charts across deployments. The charts directory holds any subcharts your main chart depends on, allowing for complex, multi-component applications to be managed as a single unit. Let's explore the powerful features that make Helm charts such a valuable tool in Kubernetes deployment management. Templating with the Go template language is one of the most powerful features of Helm charts. It allows you to create dynamic Kubernetes manifests that can adapt to different deployment scenarios. Key templating features include variable substitution from values, files, control structures for conditional resource creation, built-in functions for common operations, helper templates for reusable components. Versioning in Helm charts ensures that you can track changes and manage updates effectively. Each chart version represents a specific state of your application, enabling semantic versioning for clear update paths, release history for auditing, rollback capabilities for quick recovery, version-specific documentation. Dependencies management allows charts to rely on other charts, creating a modular approach to application deployment. This means complex applications can be broken down into manageable pieces. Common components can be reused across different charts. Updates to dependent charts can be managed systematically. Version constraints can ensure compatibility. Configuration through values.yaml provides flexibility without sacrificing consistency. You can override defaults without modifying templates. Maintain different configurations for different environments. Use the -miniset flag for quick value overrides. Merge multiple value files for complex setups. Repositories provide a way to share and discover charts. Whether using public repositories or private ones for internal use, they enable central management of chart versions, easy distribution across teams, standardization of deployments, community collaboration. Let's examine the practical applications of Helm charts in real-world DevOps scenarios, focusing on how they solve common deployment challenges. Simplified deployments represent the primary use case for Helm charts. Instead of managing multiple Kubernetes manifests separately, charts package everything needed for an application into a single unit. This reduces deployment complexity, ensures consistent resource creation, minimizes human error, speeds up deployment processes. Application packaging with Helm charts allows you to create reusable templates for your applications. This is particularly valuable when deploying similar applications across different teams, managing microservices, architectures, standardizing deployment patterns, sharing common infrastructure components. Configurable deployments become much more manageable with Helm charts. Using values.yaml and override capabilities, you can maintain different configurations for dev, staging, and production. Customize resources based on environment needs. Implement feature flags through values. Adjust scaling parameters easily. Team collaboration improves significantly when using Helm charts. Teams can share standardized deployment patterns, maintain version control over configurations, document deployment requirements clearly, review changes through normal code review processes. Public repositories extend the benefits of Helm charts to the wider community. By publishing charts to public repositories, you can share your work with others, benefit from community contributions, learn from other implementations, reduce duplication of effort. Let's explore the complete lifecycle of a Helm chart, from initial development through to deletion, understanding each phase and its best practices. Chart development is where everything begins. During this phase, you create the basic chart structure using Helm Create. Define your Kubernetes resource templates. Set up default values in values.yaml. Document chart usage and requirements. Best practices include using helper functions, implementing proper validation, and following Kubernetes best practices in your templates. Chart packaging prepares your chart for distribution. This involves updating the chart.yaml version, running Helm lint to check for issues, creating a versioned package with Helm package, generating updated index files for repositories. Remember to maintain semantic versioning and document changes in a changelog. Chart deployment is when your chart comes to life in the cluster. Key considerations include validating configurations before deployment, using -ministry run to preview changes, implementing proper resource requests/limits, monitoring deployment progress. Always test deployments in a non-production environment first. Chart. Upgrades and rollbacks are crucial for maintaining application stability. This involves testing upgrades in staging environments, using -atomic for automatic rollback on failure, maintaining upgrade documentation, validating rollback procedures. Chart deletion should be handled carefully to ensure proper cleanup. Consider using -min cascade to control dependent resource deletion, backing up important data before deletion, verifying resource removal, maintaining deletion scripts for complex scenarios. As we conclude our comprehensive exploration of Kubernetes package management, let's summarize the key concepts and takeaways from this module. We began by understanding the historical context and need for package management in Kubernetes. We learned how early manual deployments led to the development of sophisticated tools like Helm, Kustomize, and others to address the growing complexity of Kubernetes applications. We dove deep into Helm as the leading package manager, covering its core concepts and components, the structure and anatomy of Helm charts, best practices for chart development, real-world use cases and implementations, the complete lifecycle of charts from creation to deletion. Key takeaways include: 1. Package management is essential for maintaining scalable Kubernetes deployments. 2. Proper templating and value management leads to more maintainable configurations. 3. Version control and rollback capabilities are crucial for production environments. 4. Community collaboration through chart repositories accelerates development. As you move forward in your DevOps journey, remember that effective package management is crucial for maintaining consistency across environments, reducing deployment complexity, enabling team collaboration, ensuring reliable application lifecycle management. Keep exploring the ecosystem, stay updated with best practices, and don't hesitate to contribute back to the community with your own charts and improvements.